All right, so in lesson 3.5, we learned about transformations, which is basically changing a figure in some way. We learned about rigid transformations. What were the three types of rigid transformations? Give me one. Translation, which was like a slide. Rotation, which was like a flip, and reflection, which is like, oops, I said rotation was like a flip. It's not. Rotation is like a turn. Reflection is like a flip, right? Okay, so those were the three types of rigid transformations. Rigid meaning the pre-image and the image are congruent to each other. You don't change the size or the shape of the figure, just sort of the orientation of it. Today in 3.6 we're learning dilations. And dilation is not considered a rigid transformation because dilation means to change the size, either make it bigger or make it smaller. All right. So the pre-image and the image are not congruent to each other, but they are similar to each other. You may have learned about similar figures before, but basically similar figures just means if you take a figure and make it in the same proportions but larger or smaller. But you're not going to take a figure like this triangle and, then make it this triangle. That's not similar, right? That looks like a different type of triangle. So similar means that it looks like the same type of figure, just either enlarged proportionally or reduced proportionally. Okay. With a dilation, what's happening is you're going to take the sides, the length of the sides of the figure, and do the same thing to all the sides. In other words, multiply every side by 3, or multiply every side by 1/2, or whatever the number might be. This is going to change the size of the figure, right? So if you, let's say you have a photograph, and it's a 4:6 photograph, and you want to enlarge it. Well, if you double the length of every side, you're going to get 8:12, and that will be a proportionally enlarged photograph. Okay, so that is similar, right? 4:6, 8:10, everything doubled, right, or multiplied by 2. That doubling, that whatever we multiply by, is called the scale factor. So the scale factor of a dilation is how much you multiply something by. Has anybody ever had their eyes dilated? Like at the eye doctor, they put the drops in and your pupils get really big, right? So dilation, that means it's changing the size of your pupils. It's a terrible experience, isn't it? Okay, to figure out the scale factor between two figures, a pre-image and an image, what we're going to do is take the image length of one of the sides of the image, and put it over the length of the sides of on the pre-image. I like to think of this as new over old, right? The new length over the old length. And you just divide them, that'll give you the scale factor. Now, as far as notation, remember we did translations and we did like x, y becomes x plus 2, y minus 4, or whatever. That was a translation. What movement would that make if it was x plus 2, y minus 4? How would that shape move? To the right 2 and down 4, right? So that's a translation. So that's just an example of what we did before. This is a rule for a dilation. XY maps to, that arrow means, becomes dx dy. So you're multiplying every x and every y by d, and they call d the scale factor. Okay? If the scale factor of a dilation is greater than 1, then the dilation is called an enlargement. It's getting bigger. If you multiply by 2 or 5 or 25, right? Everything's going to get bigger. If it is, and I'm going to have you change these words, cross out less than 1. If it is between 0 and 1, then the dilation is a reduction. So here's a couple of examples. In this first example on the left, we started with quadrilateral ABCD with a side length of 2, and they mark A as the center of the dilation. I'm not going to worry too much about the center of dilation, but you can see how this, kind of locked in at A and enlarged off of A. ABCD becomes A prime, B prime, C prime, D prime, and the new side length that corresponds to 2 is 4. So if we do what we set up here about new over old, the new length is 4, the old length is 2, and when we simplify that, we get that the scale factor is 2. The rule for that would be xy maps to 2x, 2y, because that scale factor is 2. So on a coordinate plane, this would affect our coordinates. We'll see that in a little bit. Okay. The example on the right is an example of a reduction. It gets smaller. So it starts with EFGH. Again, you can tell that's the pre-image because there's no little primes, right? So we know we start with EFGH, and then it shrinks. This time the center is C, so it's shrinking around that center down to E prime, F prime, G prime, H prime. Now, if I do new over old, what's the length of the new figure? 2, and the old is 8. So that simplifies to 1/4. So my scale factor is 1/4. And my rule would be xy maps to 1/4 x, 1/4 y. All right, so if we look at a couple of examples, what shape is this? Number 1. It's a triangle. It starts as a triangle, it ends as a triangle. If you read the directions, it says the solid line figure, so this bigger triangle, is a dilation of the dashed line figure. In other words, the dashed line is the pre-image. It starts as the dashed, and it becomes the solid. They ask us to figure out the scale factor, so we're going to do new over old. If it starts as dashed and becomes solid, is this an enlargement or a reduction? Starts as dashed and becomes solid. Enlargement. It's getting bigger. So we're going to do new over old. What is the length of the new side of the triangle? 9. Tricky, right? Not 6. 6 is not the length of one of the sides of the triangle, right? It's only a part of it. So you have to take this whole side, which is 9. That's the bottom of the triangle, and it corresponds with the bottom of the original triangle, which is 3. So 9 over 3 gives us a scale factor of 3, and it makes sense that it's a number greater than 1 because we looked at it and we knew it was an enlargement. Yes? Okay. Number 2. Again, the dashed is the pre-image. So it's starting dashed, ending solid. We're going to do new over old. When we look at dashed to solid, are we expecting this to be an enlargement or a reduction? Reduction. So we're expecting our scale factor to be some fraction or decimal between 0 and 1. So like a half or 2/3 or 3/4 or whatever, right? So what is the length of the new side? 15, and the old is 20. Simplify that, divide top and bottom by 5, you get 3/4. So the scale factor is 3/4 or 0.75. Again, we expected that because it looks like a reduction. I can tell you that last year I remembered grading the tests on this unit, and although I knew everybody knew how to tell if it was an enlargement or a reduction, that's not really hard, right? If it's getting bigger, it's enlargement. It's getting smaller, it's reduction. And I would have a question that says, okay, here it is. Here's the pre-image. There's the image. Is it an enlargement or reduction? And they would get it right by looking at the picture. And then I would say, okay, find the scale factor of this situation. And they would accidentally put old over new or something like that. And so they would write like enlargement, and then they would calculate and get like 1/3. So I'm trying to point this out because think about, does my answer make sense, right? If it's a scale factor of 1/3, would that give you an enlargement? No. So there's a way to kind of, catch your mistakes by figuring the scale factor, looking at the diagram and say, does this make sense? Does this look 5 times bigger? I got scale factor of 5. Does it look 5 times bigger? Does this look half the size? I got a scale factor of 1/2. Okay, so just make sure your logical answer matches your numeric answer. All right, so a couple of word problems here. If you remember doing proportions in the past, right, solving proportions, you cross multiply, remember that? Okay, so that's going to come in handy for setting up proportions with scale factors. Some of these questions, I'm going to set them up as proportions just to give you that method. Some of them you could probably figure out, just by dividing or whatever. So, but just bear with me here, okay? So, the image of an eraser in a magnifying glass is 3 times the eraser's actual size and has a width of 14.4. So the enlarged eraser size is 14.4. Always think of new over old, right? The new is 14.4. The old is what we're looking for. New over old gives us the scale factor. What's the scale factor in this question? The image of an eraser is 3 times the eraser's actual size. So what's the scale factor? 3 or 3 over 1. So if you see this proportion now, you can cross multiply. 14.4 times 1 is 14.4, and 3 times x is 3x. Divide both sides by 3, and x equals 4.8 centimeters. Now, could you have just done 14.4 divided by 3? Yes. Right. But not all of them are going to lend themselves to such easy calculations. So I just wanted to show the proportion method there. All right, let's look at number 4. A square on a transparency is 1.7 inches long. The square's image on the screen is 11.05 inches long. The transparency, by the way, refers to that little sheet of clear plastic that a teacher would use on top of an overhead projector. You know, like an overhead projector, and they put that's the transparency, they put it down. And then it projects onto the screen larger for you to see, right? So the square on the transparency drawn on that little piece of plastic is 1.7 inches. When it's enlarged on the screen, it's 11.05 inches. So it's a dilation. We're trying to find the scale factor. Again, think new over old. So what's the new image? 11.05. And the old, 1.7. So in this case, we're just going to divide because we're trying to find the scale factor. So 11.05 divided by 1.7, 6.5, okay. Oops, not inches. 6.5 is the scale factor. So the image gets 6.5 times larger. Okay, this is a little bit of notation here. A dilation maps triangle LMN to triangle L prime, M prime, N prime. So we can tell what's pre-image and image here, right? MN is 14, M prime, N prime is 9.8. If LN is 13, what's L prime, N prime? So again, we're going to set this up as new over old. Let's deal with the MNs. Which one is new? 9.8, good. And then the old MN is 14. Now let's look at the LNs. Which one is new? L prime, N prime is what is new, right? And that's what we're looking for. So we're going to make that our X. And the old is 13, right? So that goes on the bottom because it's the original. All right, again, now we can cross multiply 9.8 times 13 equals, don't forget when you cross multiply, you set them equal to each other, 14x. And then you're going to solve for x, and you're going to get, thank you, 9.1 inches. Does that make sense? Just always think new over old, new over old, new over old, okay? All right, so if we put this on the coordinate plane now, so all of those were not on the coordinate plane. Number 6 puts it on the coordinate plane. A jeweler designs a setting that can hold a gem in the shape of a parallelogram. The figure shows the outline of the gem. That's this figure right here, okay? This is our original. The client wants a gem and setting that is slightly larger than what's the original. Okay, so what we want to do is do a dilation. Now, the dilation is going to be, the client wants this gem to be 1.5 times the size of the... It's really bad sound. That's going to be annoying on this video. That's okay. Okay, so we're going to have to start with our original points. I'm going to actually label these A, B, C, D, so that we have some reference here. So A we'll put at 0, 0. B is at -2, 2. C is at 1, 4. And D is at 3, 2. So those are our original coordinate locations. So let's go to part A now. Draw the gem after a dilation with a scale factor of 3/2. Now, is this going to be an enlargement or a reduction? Enlargement. Don't be fooled by the fact that it's a fraction, right? Some fractions are greater than 1. This fraction is 1.5, right? So it's actually getting 1.5 times larger, even though they wrote it as in like fraction form. Okay, so our original points are listed as A, B, C, D. Let's figure out A prime, B prime, C prime, and D prime. So if the original A was 0, 0, when we multiply both of those by 3/2, what do we end up with? Still 0, 0. B prime, though, if we have -2 as our x here, and we want to multiply that by 3/2, what are we going to get? -3. Right? -2. Think of it as over 1 times 3/2. 2's cancel. We're just left with -3. All right? And the y-coordinate is 2, so it's going to be 3. C prime. 1 times 3/2 is 3/2, or 1.5. 4 times 3/2. 4/1 times 3/2 is what? 6. Good. And D prime. 3 times 3/2, or times 1.5 is 4.5. And 2, again, is 3. So if we plot these points now, 0, 0, A prime, -3, 3 is B prime, 1.5, 6, I missed that, sorry, that's C prime. And D prime is at 4.5, 3. So you can see that the parallelogram looks like the same shape, just a little bit bigger. Okay, the client is so pleased. Now she wants to make little earrings. So the dilation this time is going to be making the original smaller. So she wants a scale factor of 1/2. Now this is 1/2 of the original. So we're going to still start with these original A, B, C, D. I'm going to mark these A double prime, B double prime, C double prime, and D double prime. So why don't you try to do that now? Cut everything in half. Okay, so you should get 0, 0, -1, 1, 0.52, and 1.51. And when you graph that, you can see that it looks like the same parallelogram, just a little bit smaller. Half the size, in fact. By the way, if you have a dilation where you multiply something by a negative number, it doesn't change the size. The negative sign does not change the size. Negative will make it reflect or rotate or something like that. Okay? It will not change the size unless you multiply by a -3. Well, now it's going to twist and turn the other direction and get bigger. But the getting bigger is the 3 that's doing that. The negative sign doesn't change the size, only the orientation. Okay, so last thing here, given the following two figures, calculate the scale factor that scales figure A onto figure B, and then we're going to do the reverse. So if we start with A as our pre-image, and it becomes B, is that an enlargement or a reduction? Reduction, right? It's getting smaller. So if you think of new over old, the new is on the B figure. Which side do we have to use? Doesn't matter. We could pick any side we want. Well, let's use 5. So new is 5. Now when you go to A, the old, you got to make sure you're picking the side that corresponds to the 5. So now it does matter which side you use. Which side corresponds with the 5? 15, right? That side, 15, became the side that is 5. So new over old, 5 over 15, is 1 over 3. That makes sense that it would be a reduction. Oh, it's 1/3 between 0 and 1. All right, now imagine it in the opposite direction. We're going to start with B, and it's going to become A. So new over old, let's pick a different side. Starts with B, ends with A. Our new is going to come from A. Let's use 12. If I pick 12 as my new, what's my old? 4. 12 over 4 simplifies to 3. So this is a scale factor of 3. From B to A, is that an enlargement or a reduction? Enlargement. Notice that if you had picked a different side, 2 over 6 is 1/3, 3 over 9 is 1/3, 4 over 12 is 1. It doesn't matter which side you pick. If it grew proportionally, then all the sides will have the same scale factor, same ratio. Okay, what's the relationship you see between the two scale factors? How would you describe these two numbers and how they relate to each other? 1/3 and 3, what are they? They are reciprocals of each other. Which makes sense, right? Because it's kind of like new over old both times, but in one case the new is the smaller one, and then in the other case the new is the bigger one. So it makes sense you're just sort of flipping it upside down. Okay, so dilations, enlargements, reductions, scale factors, coordinate plane. Any questions?